Good day, Damians. This is your General Mathematics teacher, Ms. Mary Christine Gamuzon Tolan. And for this week's video, we will be talking about rational functions. We have two goals for this week's lesson, and these are: first, we are going to define a rational function, and second, we are going to solve for its domain, range, asymptotes, intercepts, and zeros. Enjoy learning! So to start with, let us define what is a rational function. A rational function is a function that can be written in the form f of x is equal to n of x over d of x, where the numerator, n of x, and the denominator, d of x, are polynomials, and d of x is not a zero polynomial. So it is very important that d of x is not a zero polynomial, because if it is, then our function will be an undefined function. So we have to avoid making d of x, or the denominator, be equal to 0.
Now let's identify which of the following functions here can be considered as rational function. Let's examine letter A. So f of x is equal to 2 plus x all over x plus 1. So both numerator and denominator here can be considered as polynomial, particularly linear. So therefore, this can be considered as rational function. For letter B, we have g of x is equal to x squared minus 4x minus 5 all over x plus 3. So the numerator is particularly a quadratic and the denominator is a linear. So both are polynomials, and therefore this can be considered also as rational function. Now for letter C, we have h of x is equal to square root of x plus 2 all over x raised to 1/2 minus 4. So square root of x means x raised to 1/2. This means that the given numerator and denominator here are not considered as polynomials, since they are having an exponent that is a fraction. And therefore, since the numerator and denominator are not considered as polynomials, this is not a rational function. For letter D, we have I of x is equal to the square root of 2x all over 3 plus x. Although we have here a ratio, but we should not disregard the radical sign. And the radical sign here makes this as a radical function. And therefore, this is not also a rational function, but a radical function.
Now let's talk about the domain of a rational function. So the domain of a rational function, f of x is equal to n of x over d of x, is the set of all values of x that will not make d of x be equal to 0. So all those values that will make our d of x, or the denominator, be equal to 0 is the restriction in our domain. For the range, we can find the range of a rational function by first getting the inverse of the given original function, and secondly, we are going to identify its domain, because in that way, the domain of the inverse of a rational function is the range in the original function.
Now let us going to identify the domain and the range of our given rational function. So the given rational function here is f of x is equal to 2 plus x all over x plus 1. So it says that in getting the domain of any rational function, we will equate whatever the denominator is to 0, and we are going to solve for x. That value of x will be the restriction in our domain. So solving for the domain, we have the denominator x plus 1. We equate it to 0, and so x is equal to -1. So our rational function here can take all values of x except -1, because if we will substitute -1 into our function here, this will give us a 0 denominator that will give us an undefined function. And therefore, for the domain of our rational function here, we say that it can take all values of x except -1. And so now we are going to solve for the range of our rational function. So it says that in solving for the range of a rational function, we will get its inverse first, and we will identify the domain of that inverse. In that way, that domain of the inverse is the range of our original rational function. So to do that, we will follow the 4 steps in getting the inverse. First, we are going to change f of x to y. So we have y is equal to 2 plus x all over x plus 1. This will be followed by interchanging x and y. So we have x is equal to 2 plus y all over y plus 1. Since we have here a fraction, and we all know that this x here has a denominator 1, we will cross multiply x by y plus 1 and 1 by 2 plus y. So this will give us xy plus x is equal to 1 times 2 is 2, 1 times y is positive y. So now we will be regrouping all the terms with variable y on the left side of our equation and all of those which do not have a variable y on the other side of the equation. Now, after regrouping, we will factor out y from the expression xy minus y. So, we have y times x minus 1 is equal to 2 minus x. And since we are just looking for y here, we will be dividing both sides of the equation by x minus 1. So, we can now cancel x minus 1, leaving us y is equal to 2 minus x over x minus 1. So we were going to change y to f to the negative 1 of x. And we have here 2 minus x all over x minus 1. So this is also a rational function, and it has a restriction in the domain where our x should not be equal to 1, because if we have here x is equal to 1, 1 minus 1 will be 0. So therefore, this is now the restriction in the domain of the inverse of the rational function 2 plus x over x plus 1. And since this is now the domain of our inverse, this means that this is now the range of the original rational function. Therefore, the range is all values of y except the restriction positive 1. Now for the second example, we are given here a rational function r of x is equal to 2x all over x plus 3. So to solve for the domain of this rational function, we will be equating the denominator x plus 3 to 0, and we are going to solve for x. So to do that, we have the denominator x plus 3 is equal to 0, and so x is equal to negative 3. So this is now the restriction in our domain. This means that this rational function here can take all values of x except negative 3. Now, to solve for the range, we will try to solve the inverse of this rational function, and we will get its domain to be the range of our original function r of x. So to do that, to the negative 1 of x is equal to negative 3x all over x minus 2. So since this is a rational function, this means that it has a restriction in its domain. Here, x should not be equal to 2, because if x is equal to 2, this will give us a 0 denominator. And so, since this is now the domain of our inverse, this will serve as the range of the original r of x. And so therefore, the range here is all values of y except 2. let us try to solve for the asymptote of our rational function. So we are given here rational function m of x, which is equal to 2x plus 4 all over x minus 1. So to solve for the vertical asymptote, we will be needing the denominator x minus 1. And then we will equate this to 0, and we will be solving for the value of x. That value of x there is already our vertical asymptote. So vertical asymptote is x is equal to 1. Now, in identifying the horizontal asymptote of our rational function, we need to identify the condition that the given rational function belongs to, considering the degree. So we have here three conditions. If the degree of the numerator is lesser than the degree of the denominator, we will have our horizontal asymptote y is equal to 0. On the other hand, if the degree of the numerator is just equal with the degree of the denominator, we will have the horizontal asymptote y is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. And lastly, if the degree of the numerator is greater than the degree of the denominator, we have no horizontal asymptote in that case because we will be having an oblique asymptote. So now let's try to examine where does the function m of x belong to. So we have 2x plus 4 all over x minus 1. So considering the degree, both have exponents 1. And so therefore, they are just equal. N is equal to m. We belong to this condition number 2. So to solve for the horizontal asymptote, we will be having y is equal to a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. So the leading coefficient of the numerator is 2, and the leading coefficient for the denominator is 1. And so therefore, y is equal to 2 over 1, and that is 2. For the second example, we have here m of x is equal to x plus 7 all over x squared minus 1. So to solve for its vertical asymptote, again, we will be needing the denominator and we will equate it to 0 and let us solve for x. So the denominator is x squared minus 1, equating it to 0, x squared is equal to 1. So since we need to solve for x, square root of x squared is equal to square root of 1. And so x is equal to positive and negative 1. So therefore, the vertical asymptotes here, we have 2. X is equal to 1 and x is equal to negative 1. So we have 2 vertical asymptotes for this rational function. On the other hand, for our horizontal asymptote, we will consider the degree of our numerator and denominator. So let n be the degree of our numerator and m be the degree of our denominator. So it shows that our numerator has the exponent 1 while our denominator has the exponent 2. And therefore, n is lesser than m. And if we have this condition, it follows that our y, or the horizontal asymptote, is equal to 0. So therefore, we have here the horizontal asymptote is y is equal to 0. So this is from condition number 1. Now for the final example, we need to find the vertical and horizontal asymptotes of our rational function p of x, which is equal to x squared plus 2x plus 1 all over x. So for the vertical asymptote, we need to equate x to 0. So x is equal to 0. That's it. For the horizontal asymptote, we need to consider the degree of our numerator and denominator. So let's say n is the degree for our numerator and m is the degree for our denominator. So the degree of our numerator here is 2, and for our denominator we have 1. And therefore, n is greater than m because 2 is greater than 1. And it follows that if we have this condition, we have no horizontal asymptote for this rational function. Instead, we will be having an oblique asymptote. Now, to solve for the oblique asymptote, we need to divide our numerator by the denominator. So we may choose to perform the long division or the synthetic division. So if we are going to perform the long division, we have x squared plus 2x plus 1 divided by x. So x squared divided by x, that would be x, because x times x is x squared. So subtract x squared minus x squared is 0. So we will now bring down positive 2x. So 2x divided by x, that will give us positive 2. So 2 times x is positive 2x. Now we are going to subtract, and this will give us 0. And then we will bring down positive 1. And since we cannot divide 1 by x, so this means that this is now our remainder. So according to the rule, we are going to disregard our remainder, and we will equate our quotient to y. And that is now our oblique asymptote. So y is equal to the quotient, which is x plus 2. So this is now the equation for our oblique asymptote. On the other hand, if we will be using the synthetic division, we will consider the coefficients of our numerator. So for x squared, we have 1. For 2x, we have, of course, 2. And our constant 1. For the value that is inside here, we will equate the denominator to 0. So equating the denominator to 0, we have x is equal to 0. So therefore, we have the value 0 here. Now we will bring down 1. So 1 times 0 is 0. And bring down 2. 2 times 0 is 0. So we have 1. So this is now the remainder. This is now our constant, positive 2. And this is now the coefficient for our variable x. So we have x plus 2. So we will equate x plus 2 to y, and that is also our oblique asymptote. So this coincides with our oblique asymptote a while ago using the long division process. Now let's try to find the zero of these following rational functions. So to solve for the zero or the roots of a rational function, we need to solve for the value of x that will make our numerator be equal to 0. So to do that, we need to equate the numerator to 0. So we have x squared plus 2x plus 1 is equal to 0. And then we are going to solve for the value of x. We need to find the factors of our trinomial here. And we have the factors x plus 1, x plus 1. And so therefore, we will be equating these factors to 1. And since they are just identical, we can just equate x plus 1 to 0, and x is equal to negative 1. So this is now the 0 for our number 1 function, p of x. So we have x is equal to negative 1. Now for number 2 example, we will be equating our numerator x squared plus 6x plus 8 to 0. So x squared plus 6x plus 8 is equal to 0. So this has factors x plus 2 and x plus 4. So now let us equate each of the factors to 0. So we have x plus 2 is equal to 0. And x plus 4 is equal to 0. It follows that x is equal to negative 2 and x is equal to negative 4. But in this case, we need to be very careful because considering our denominator, where we get our restriction in our domain, it shows that our denominator has the factors x minus 3 and x plus 2. So getting the restriction in the domain, we have the restrictions x is equal to 3 and x is equal to negative 2. And so therefore, it shows that negative 2 here is already a restriction in our domain. So it cannot be that it is both a restriction and at the same time a 0. So negative 2 here is a restriction instead of being a 0, and therefore the only 0 in our rational function here is negative 4. So let's now try to find the intercepts of our rational function p of x is equal to x squared plus 2x plus 1 all over x. So let us try to solve first for the y-intercept. So in solving y-intercept, we need to substitute 0 for our x variable. So p of x will now become p of 0 is equal to So since we are having a 0 denominator here, which will give us an undefined answer, it means to say that this rational function has no y-intercept. Now let's proceed with the x-intercept. So x-intercept, so in solving for the x-intercept, we need to equate y to 0, or we need to substitute 0 to our y or to our p of x. So this will give us 0 is equal to x squared plus 2x plus 1 all over x. Now, since we are having a fraction here, we need to have a denominator 1 for our 0 to do cross multiplication. So 0 times x is 0 is equal to 1 times x squared plus 2x plus 1, which will give us x squared plus 2x plus 1. And so we are going to factor out this trinomial here to get the value of x. So factoring out, we have x plus 1 times x plus 1 is equal to 0. So this will give us, since they are just identical, we will equate x plus 1 to 0, and therefore x is equal to negative 1. So this is now our x-intercept. Now for number 2 example, we have the rational function f of x is equal to x plus 8 all over x minus 2. So let's solve first for the y-intercept. And we will be substituting 0 for our x variables. So y is equal to negative 4. This is now our y-intercept. Now, to solve for the x-intercept, we will substitute 0 to our y variable. And therefore, this is now our x-intercept.